All right, good evening. Welcome back to differential equations. We're going to do some more with Laplace transforms. Okay, so in times where we would be in person, one of the things I would ask us to do at the end of the class where I did this would be for you to do your own Laplace transform. And I would do something like, hey, why don't we do cosine, I'll say of 2t, okay, and b would be the hyperbolic cosine of 2t. Okay, so the astute student would know. Okay, I had a friend that when I worked at Ball, we would joke that when he went to school, instead of things like the remainder of this proof is left as an exercise for the reader kind of stuff, his math books, his math teachers would say things like the astute student would notice, and neither of us were the astute student. Okay, but this is actually the easier of the two problems. Okay, let me spell them out for you a little bit. This one, right, if we take the Laplace transform of cosine of 2t, right, what we're going to get, okay, is we're going to see integral from 0 to infinity e to the negative st cosine of 2t dt. You see, that looks delightful because we're going to have to do integration by parts twice. And then you're going to have to take one of them and swing it to the other side, so you could factor out the integral and then solve for it and actually get an answer. Okay, I'm sure you remember all of that from Calc 2 and all of its delightful promises there. This one is the same setup, right? E to the negative infinity, e to the negative st, cosh of 2t dt. And you might think it's going to be the same thing with the integration by parts, swinging it from, doing it twice, swinging this from one side to the other side, and then factoring and multiplying. And with cosh, it might actually be a little bit easier to do it that way because the derivative of sinh is cosh, and cosh is sinh, so, not as much of a problem. But what we're going to do here is we're going to go back to the definition for cosh and say that this was, right, e to the negative st times, right, and this is e to the 2t plus e to the negative 2t all over 2, okay, dt. And what that lets us do, 0 to infinity, is we could separate things out. We could take the 1/2 out in front, right? We could say this is e to the negative st times e to the 2t, right? And then plus e to the negative st times e to the negative 2t, right? And we could even break it around this further by, making this two integrals, because that's really what we're going to be doing anyway. Right, dt, and then going off and doing it this way. So what's our next step here? The next step is to say this is 1/2, and we're going to combine exponents. So this is integral from 0 to infinity. This is e to the negative s plus 2 t, right? And again, 0 to infinity, e to the negative s minus 2 t. Okay? dt's. All right, now, one of the things that's really great about calculus, because I noticed that some of you guys make some mistakes where I really wish you weren't making them, but it builds on skills that you already have. Okay, so if you need to do this, let a equals negative s plus 2, and b is equal to negative s minus 2, and you want to rewrite this, okay, as 1/2 integral from 0 to infinity of e to the at plus 0 to infinity e to the bt. You go right ahead and do that, okay? I always remember, I don't know, 4th or 5th grade teacher, and we'd have to do something like this. And I mean, that's, today, what do you guys do, right? You really pretend this is 20, so you get 43, and then you add the 1 back in, and you get 44. At least that's the way you're supposed to be doing it nowadays. So you'll minus 1 plus 1, so this is 63 minus 20 plus 1, so it's going to be 43 plus 1 is 44. That's 21st century new math. What is it? Common Core, that's what they call it these days. Okay, great. But back in the day, right, we would borrow, right? We would give a tens unit to this because it was smaller, and then make this one tens unit smaller. So 13 minus 9, we get 4. Hey, what do you know? Same thing. But I did have a teacher that's asked me, he says, why do you do this? Like, well, that's the way I was taught how to do it. Like, well, aren't you confident enough to be able to do this? So let me tell you that back when I was in the grade school, I was not the astute student. Okay, they divided us up into like the gold group, the silver group, the bronze group, and lower. So I was like in cadmium. Okay, we watched the Olympics. We knew gold was best. We knew they weren't fooling us. Okay, we knew. So if I could vocalize it now, right, to this teacher, I'd tell him, like, look, this is working for this kid. Okay, just let him do it. It's fine. So if you want to make some substitutions to make your life a little bit easier, so you can recognize these problems and you don't get kind of bogged down with all of this, okay, you go right ahead and do that. All right, there's nobody's going to look, nobody's going to know. All right, we're not going to know. It's going to be just fine. And if it helps you get the right answers, it helps you do the problems, like, they're more, they're within your grasp. It makes it easier for you to do them or see them. And go right ahead. Okay, and nobody's going to judge you for doing this. I mean, fifth grade teacher might, but the important thing is you could say the words, I could take the Laplace transform of this function. That's the goal. All right, so if you have to do it a couple extra steps and somebody else next to you, like, you're still taking the Laplace transform. You're still doing great. So don't worry too much about that. This is going to go from 0 to infinity. I just integrated these things. If you want to take the derivative of this whole thing, right, don't forget your chain rule, but the a's are going to cancel, the b's are going to cancel, life is going to be good. Okay. So one of the things we have to deal with, right, is that these integrals have to exist. And the only way these are going to exist, okay, is if e to the at, right, as t goes to infinity, e to the at goes to 0. Okay, as t goes to infinity, e to the bt goes to 0. Okay, that's how these integrals exist. Okay, I suppose they can go to a different number, but I can't think of how that's going to work if a's are constant and t is going to infinity. Okay, so the only way this is going to work is a has got to be less than 0, and b has got to be less than 0. Okay, remember where we got this stuff from, right? This was negative s plus 2. That's got to be less than 0. This was negative s minus 2. It's got to be less than 0. All right. So let's see. We have negative s less than negative 2. So s has to be greater than 2. This is negative s less than positive 2, right? Adding 2 to both sides. And then stripping out the negative, and what happens when you strip the negative is you change the sign. We'll take the more restrictive of the cases. This has got to be bigger than 2. Okay. So if a is negative, b is negative, then when I go through and do this, right, this is 1/2. We've got 1 over a here, and I've got e to the a capital T, that's my limit, as t goes to infinity here, minus e to the 0, which is 1, okay, plus 1 over b. Here we've got e to the bt, right? This is, again, limit as t goes to infinity. Okay, minus again e to the 0, which is 1. All right, then what we have here is a 1/2. Here's a 1 over a. This is a 0 minus 1, isn't it? Plus a 1 over b. And again, this is a 0 minus 1. Okay. So that's what we have. We have a negative. Don't want to do a negative. We might put this negative back in. Okay, we have a 1 over a plus a 1 over b. Okay. And all I'm going to do is I'm going to get common denominators here. Okay, so we can see what's going on. I'm going to back substitute in a minute. So we have negative 1/2. Okay, we have a over ab plus b over ab. All I did is I multiplied by a over b to get common denominator, a over a to get common denominator. So this is negative 1/2. Here we have a plus b over a times b. What was a? What was b? Okay. A was what was a? A was all the way back up here, wasn't it? A was negative s plus 2. Right, so we have negative s plus 2. There's my a. Okay, plus. We have negative s minus 2. Here we have negative s plus 2, negative s minus 2. Okay, we got to simplify this a little bit. So this is 1/2, negative 1/2. We have negative s plus negative s. That's negative 2s. Boy, that's convenient. Here we have, right, here's a 2, here's a minus 2. So plus 2 minus 2. So that's out. And then we got to deal with this. Right? So negative s times negative s, that's s squared. We have minus 2s, right? You can see these are conjugates, right? Plus 2s. Okay, and then that's minus 4. So that's going to be, right? That's going to be the negative times this negative will make it positive. We have a 2 and a 2, so that's going to cancel. We have s over, we have s squared minus 4. Okay, so the Laplace transform, right, of hyperbolic cosine of 2t is equal to s over s squared minus 4. This 4 is because of this 2. So if we could generalize this, right, this is Laplace transform of cosh of at, right, to put anything in there you want, or alpha t or whatever, that's going to be s over s squared minus a squared. Okay, that's the Laplace transform of this. Now, after we're done with this section, you are allowed to use a table. I will provide this to you. Okay, so you're going to see this on your exams. You're going to see this. You can use this on your homework. All right. So you were encouraged to use this. So if we go back down here, we find cosh at, right? We get s over s squared minus a squared. Beautiful. All right. And I want you to be able to deal with it. Okay. Now, here's why I'm a jerk. Okay. And I get this from the way I grew up too. So we want to do the Laplace transform e to the negative st of cosine of 2t. Now, most of the students are going to dutifully go through and do integration by parts twice and do the whole, flip this over to that and deal with it. But I'm going to bring your attention to something. I'm going to say, well, remember cosh of 2t was equal to, actually, let's just do cosh of x. Okay, that way it'll keep everything kind of simple. So we just do cosh of x, which is 2t. That was e to the x minus e to the negative x over 2. Well, you ever wonder, like, this cosine, hyperbolic cosine, and this cosine, like, why did they call it the same thing? Well, cosine of x is equal to e to the ix minus e to the negative ix over 2. Okay, if you're going to do sine, okay, so here's sinh. Okay, this was e to the x. Oh, there's a plus in here. What am I doing? I wrote down sinh rather than cosh. Okay, this is e to the x minus e to the negative x over 2. But sine x is equal to e to the ix minus e to the negative ix over, it's a little different, 2I. Okay, so if you're ever wondering, like, why is it cis? Why is it cosine theta plus I sine theta? This is because the I cancels with this I. Okay, so yeah, that is how the relationship between sinh and sines and coshes and cosines go. Now, we can use this, okay? I is a constant. So if I want to deal with cosine of 2t, we can say this is e to the negative st, right? We're going to integrate from 0 to infinity. And instead of doing that, we can say, well, this is going to be e to the ix plus e to the negative ix over 2. I'm sorry, t's. Let's go back to t's. Actually, x is, in this case, x was what? X is 2t. So we'll go back in a minute. Okay, let me clean this up and say we have 1/2. That's the 2 here. 0 to infinity, e to the negative st. And here we have it. We have e to the I, 2i, right? T plus e to the negative 2it. All right? And we're just going to treat I as a constant because it is. All right? So same deal as what happened before. We're going to say this is 1/2, integral from 0 to infinity, e to the negative s plus 2i t, right? Plus, because it's cosine, okay? E to the negative s minus 2i t, all right? And we're just going to proceed just like we did with hyperbolic cosine, all right? S does not have any limitations on it, right? We could say S is whatever we want it to be, as long as this integral is going to converge. So if you want to say, well, S is equal to, you know, in this case, right, in this one over here, you want to say S is equal to 3 plus 2i, right? So we have negative 3 minus 2i plus 2i. That integral is going to converge. That's fine. Okay. So you're allowed to set t, or set s rather, to anything you'd like. I'm not going to worry about it just yet, though. Okay, we're just going to know that we can set it to be anything convenient. Okay, as long as the interval converges, it's the only thing that matters. Okay, there's going to be one other time where we use complex numbers, by the way. So let's just go through this the same way we did before. Okay, I'm going to go ahead and say let A is equal to negative s plus 2i. Okay, B is going to be negative s minus 2i. Okay, so this is going to be 1/2 integral e to the at plus e to the bt, okay, dt. And we're going to end up with 1 over 2, and then we have 1 over a e to the at, right, plus 1 over b e to the bt. We're going to go from 0 to infinity. Okay, so 1/2. We have 1 over a. We have e to the a capital T. This is my limit as t goes off to infinity. Okay, minus e to the, when t is 0, you know, complex number times 0, still 0. All right. Oops, I wanted to do that. Plus 1 over b. Okay, this is e to the b capital T, because I'm taking my limit as t goes off to infinity. That's the notation. I made this up. Don't use this and expect other people are going to know what you're talking about, because they're not. Okay, e to the 0. Okay, same thing is going to happen here, right? This is just 1, so this is 1/2. We have 1 over a. We have 0 minus 1, right? We have plus 1 over b. We have a 0 minus 1. Okay, same reasoning. This integral has to converge. In order for it to converge, right, there's limitations on what has to happen here. But as long as it converges, we're happy. Okay, so this is 1/2. And again, we have, I'll put the negative out, right, because we have negative times negative. We have 1 over a plus 1 over b. So this is going to be negative 1/2. Get common denominators. We have ab over a plus b. Right? So same argument, same arithmetic, same algebra, same as everything else that we just did. Right? So this is equal to negative 1/2. What was a? A was negative s plus 2. Oops, I got the wrong ones, right? This was b, this was a plus b. This one was a plus b. Denominator is ab. Okay. Sorry about that. All right, get my common denominators good. All right, so this was s, negative s, what was this, plus 2? That was over here. Okay. 2i. All right. And here we have, this was negative s minus 2i, so this is going to be minus s minus 2i all over, and then we got to multiply them together. So minus s plus 2i minus s minus 2i. Okay. So on the top, it's kind of nice, right? Because positive 2i, negative 2i, that goes away. And we just end up with a negative 1/2. We have a negative 2s up here, so everything conveniently works out. Here we have negative s times negative s, s squared. Okay. We have 2i minus s, so that's minus 2is. We have negative times negative, so it's going to be positive 2is. Boy, that's convenient. Okay. And then the last term is going to be positive times negative, so minus. We have 2i times 2i, that's 4i squared. All right. So 2's cancel, negatives cancel, so we just have s over, I have an s squared minus 4i squared. I'm going to ask if you remember, like what was I squared? Isn't that negative 1? So really what we have here, right, is s over s squared plus 4, and that is the Laplace transform of cosine of 2t. And again, this 4 is because of that too. So if we want to do the Laplace transform, right, of cosine, say, omega t, all right, that is going to be s over s squared plus omega squared. Okay. So again, in the next section, when we have to do this backwards, we don't do inverse Laplace transforms by hand. We look them up and we say, oh, here's cosine, s over s squared plus a squared. Well, if we see a Laplace transform that looks like this, we know that going backwards, right, is going to give us, going backwards is going to give us this thing back. Okay. We'll be doing a number of examples until you get the hang of it, but it's really not so bad. Okay. But let's go ahead and keep that sheet clean. Okay. I'll go back to my other thing. So that is how you take the Laplace transform of cosine, and there's nothing wrong if you like integration by parts. You want to do it twice and swing it over and do the arithmetic and algebra. You go right ahead and do that. Okay, they're both correct. So I just wanted to show you this because I think it's a little bit easier, but you can have a difference of opinion. It's okay. So that is the worksheet that I would have given people. Okay, and again, I put a couple extra steps in there just to keep things, so it was easy to follow. But if you did, that's great, and if you didn't, that's great too. But that's how that would have worked. Okay, so I'm going to go ahead and leave it there, and we will do another one in just a moment.